By the time you are done with this unit, and maybe even with this screencast, you should be able to find the pH of the solution that is the result of a titration at any point along the line, at any point during the course of that titration. In this particular example, we have a weak acid, which we are titrating with a strong base. And if you look at the language carefully, it says the titration of the weak acid with a strong base. So that would mean that in our flask, and I'm just going to make it a beaker for reasons that I'll mention later. There's my beaker. Let's say that this is my burette. Here's the valve, the stopcock. And in here, we have our strong base, and in here, we have our weak acid. This is what it means to titrate a weak acid here with a strong base here. Another way to look at this is to think about a titration as playing a game, so to speak, called What's in the Beaker, or what's in the flask. What kind of ions and molecules are in there? Of course, there's going to be water molecules. We're going to ignore them, and we're going to ignore any autoionization of the water, because if only 2 water molecules per billion ionize, that's very insignificant compared to everything else. Now, when we open the valve right there, and I should say before we open the valve, the only ions of note that we have in solution are the weak acid. So we're going to have a few H pluses, a few of the anions. For example, acetate from acetic acid as a weak acid, the conjugate base of the weak acid, if you want to call it that. And we're going to have a lot of weak acid molecules. And I'm going to write the weak acid molecule as HA, where A is the anion and H refers to the proton. Now don't laugh at that. So you're going to have very few H pluses, very few conjugate base ions or anions, and a whole lot of weak acid molecules, because that's what it means to be a weak acid. To be a weak acid means that your weak acid, when it's by itself, is mostly going to stay weak acid, and only a little bit of it is going to become the hydrogen ions and the anions, very few of them. So you're going to have lots of this and just few of that. So this is what we have before titration. Before we even begin to add base, what's in our beaker? H pluses, otherwise known as protons, anions, but mostly, besides water molecules, we have weak acid molecules, like acetic acid. So when we look at our chart, and we look at a comparison of my hydrogen ions, or hydronium ions, the protonate, and my hydroxide ions, and my salt, because remember, an acid plus a base makes a salt plus water. We're going to have some of these. We're not going to have any of these yet. We haven't added any base, and so we're not going to have any salt yet. Now, how do we find the pH of a weak acid solution? Well, what we're going to do is we're going to take my equation right here, and we're going to write my equilibrium expression. We're going to put the products in the numerator, and my weak acid, instead of WA, we could also call it HA. There's my weak acid in the denominator, and my equilibrium expression is the products over the reactants. Now, because the only thing in the beaker is weak acid, that means that the number of hydroniums and the number of anions is the same. We can call them both X. So that means we have X squared in the numerator. And when I take the square root of both sides, I get this equation right there. So anytime you're trying to find the hydronium ion concentration, that's X. Anytime you're trying to find the hydronium ion concentration, all you need to do is to take the square root of your weak acid constant, like the Ka for acetic acid, for example, times the molarity of your weak acid solution. And then you multiply the two, take the square root. Now you have the hydronium ion concentration. And then, of course, to find the pH, you take the negative log of that. So that's how you find the pH before titration begins. And basically that was covered in chapter 17. Shouldn't be anything new there. So I'm going to erase all of this. And don't like any spurious marks. It's got to be clean. Now, let's talk about before we reach the equivalence point, right here. The equivalence point, of course, in a curve, if I sketch it in very small right here, so here is the strong base that we're adding to my weak acid molarity. My curve is going to begin with just the pH of the weak acid. And then as I add more and more base, it's going to jump up. And looks like this thing is automatically going to turn that into a straight line. Don't like that. Try again. And down here, this is the base that we're adding, I should have said. This is the base that we're adding. And my resulting pH. So if we're starting with no base added right here, I do not know why this is doing that. We're starting right there. And whatever the pH of the solution is, and as we add base, it kind of goes up ever so slightly, and then it's going to skyrocket, and then it's going to level off. So here's part 1, corresponding up here. Here's part 2 along this plateau, right there. Right there is part 3. And then part 4 is everything after that. That's part 4. So that's what our titration curve is going to look like. Let me erase that. And we will go back to looking at, we've done this, looking at before we reach the equivalence point. So now we're starting to add some base to the solution. And as we're adding some base, we have, of course, lots of hydroniums, not lots in comparison to the number of weak acid molecules, but we do have a significant number of hydroniums. And even though we're adding hydroxides, every one of those hydroxides is going to be neutralized by a hydronium to make water and also to make some salt. But that salt that it makes, there's not much salt that you're going to be making, because after all, if you think about, let's say, what if your base was a strong base and you had the weak acid of acetic acid, you recognize that your salt's going to be sodium acetate. And so that's a very soluble salt because of the sodium. So you are going to be making some salt, but the salt is not going to have much effect compared to everything else that you have in the beaker. So that's why I said that whatever happens with the hydrolyzation of the anion, remember the spectator ions don't hydrolyze, but whatever hydrogenation or takes place, I don't mean hydrogenation, I mean hydrolysis with water takes place with your anion, is going to be insignificant. And so how do we find the pH of that? Well, this is where this equation right here comes in handy. If I take this equation right there, that's the expression for my equilibrium constant, and I solve this equation for hydroniums, I get this equation right here. Now, if I take the log of both sides, the log of the hydronium becomes this, and the log of this is right there, and the log of this is right there, because if you remember anything about logs, the log of AB equals the log of A plus, the log of B. So that's how we get that. And over here, if you remember that the log of A over B equals the log of A minus the log of B, that's how we get this statement right here. We break this up into these two parts. Then the next thing we're going to do is multiply through by -1. In other words, change the sign there and there and there and there. And now we have this equation right here. And here we're going to recombine this. If I have the log of the anion molarity minus the log of the molarity of the weak acid, I can express it like this. And this equation right here is called the Henderson-Hasselbalch equation. And it is very, very, very helpful. This is the equation you're going to use to find the pH during a titration from the moment you start adding your acid or base until you reach the equivalence point. This is a great equation to understand how to use effectively. Okay? Now, one thing we ought to point out, and that is that at some point during the titration, the molarity of your anions will be the same as the molarity of your weak acid. In other words, if you started out with a mole of weak acid and you neutralize half of that, you're going to have half a mole left of your weak acid and a half a mole that has been combined with the cation from the strong base, and therefore your numerator and denominator will equal each other. And when they equal each other, you have this number equals this number, which means it equals 1, and the log of 1 is 0. The log of 1 is 0. In which case, this Henderson-Hasselbalch equation ends up being this. pH equals the pKa. Where is that on the curve? If I do my titration curve that looks like this, it's the halfway point between start. Here's my halfway point. Halfway until you reach the equivalence point, you don't even need to bother to do any math other than this. You want to find the pH, you take the negative log of the Ka, and that's your half titration point. All right, next, I'm going to do some more erasing here. Some of you are speeding through your screencast. And now we're going to look at what happens at the equivalence point. How do I find the pH at the equivalence point? Well, at the equivalence point, all of your hydroniums in the acid, and remember, as you titrate a base, this reaction keeps going to the right because you're removing the few hydroniums. Remember these few hydroniums? There goes the beaker. Remember the few hydroniums that were in solution? As you start adding base, you're adding hydroxides, and those will be making water molecules. So it's like you're removing hydrogen ions from the reaction. You're removing these from the reaction, and Le Chatelier's principle says the reaction will go to the right to help to replenish the supply. And so pretty soon, all of your hydroniums will be neutralized by your base. They sort of cancel each other out at this point, which means they no longer contribute to the pH. And when they no longer contribute to the pH, the only thing that's left is what used to be insignificant. Up until this point, the hydrolysis, of your anions or cations, depending on what you're titrating, is really insignificant compared to the presence of hydroniums and hydroxides. But at the equivalence point, they're the only game left in town. It's kind of like saying after two armies fire all their missiles and cannonballs at each other and have neutralized each other, the only thing left are sticks and stones to do battle with. I don't know if that's a good analogy or not, but it'll have to do. So let's come down to number 3. In number 3, this is where I have to use a different equilibrium expression. My equilibrium expression is right there because the only thing that's left now to affect the pH is the hydrolysis of my conjugate base, is the hydrolysis of the anion. And so my anion is negative. It'll take the place of the hydroxide, which is negative, and I get HA as a result, and the displaced hydroxide then is now present to affect the pH. And if you think about it, if we are doing a weak acid and a strong base, you expect that the pH at the equivalence point will be greater than 7 because strong wins out over the weak. So this is why when you get to this point, you have to use a different equilibrium expression than we did in step way up at the top when we were looking at just having the weak acid in solution, number 1. Also, that means now I have a different equilibrium constant expression. Here's my, I should call this the equilibrium equation, and here's my equilibrium expression. And so we put the products over the reactants. And you can see now that I take the molarity of my weak acid and my hydroxides and my anions, and I'm going to solve this equation for OH and then take the negative log of the OH, and that will give me the POH. And I'll have to subtract that from 14 to get the pH. So finally, we want to look at what happens when we are past the equivalence point. And after we're past the equivalence point, we're still adding base, and since we're still adding base, there's no more acid to neutralize it. So we're adding hydroxides. And once you start adding hydroxides, whatever hydroxides you might make from the hydrolysis of an anion are really insignificant. They're not going to show up to 2 significant digits, or maybe not even to 3 significant digits. So all you have to worry about are these, the excess hydroxides. And so what we do in step 4 is once all my moles of acid have been neutralized by my moles of base, and of course your moles of acid will be your volume of your acid times the molarity of your acid. This would be the volume of all the acid you had in the beaker to begin with, and the original molarity of the acid. That gives you your moles of acid. So therefore, when it's neutralized, that's the same as your moles of base. And if you know the moles of base, that's going to be equal to the volume of the base that you've added times the molarity of the base. So whatever volume of base you add after this volume is now where you're going to find the moles of hydroxide that you're adding. So whatever excess base you're adding, the excess volume of your base times the original molarity of that base, because the molarity hasn't changed, gives you your excess hydroxides. And the thing that most students often forget, if they do forget something, is now you need to divide by the total volume. The total volume would be the volume of all your original acid plus the volume of the base that you added to neutralize it, plus the volume of the base that you're adding after equivalence. And that's because your excess hydroxides are in this much water. Hopefully that'll help you to be able to find the pH of a solution when you are titrating an acid and a base. In this case, we were titrating a weak acid with a strong base. You just reverse everything when you're doing a weak base with a strong acid.